Welcome back to the Cave of Science, and today we're going to look at some principles of electron arrangement. The first one is the off-bow principle, and this one states that the lower available shells or energy levels must be filled before you start moving up into higher energy levels. The 1s subshell is filled before the 2s and so forth. And this will allow the electrons of an atom or an ion to form the most stable electron configuration possible. The example we have here is oxygen, atomic number 8, has 8 protons, 8 electrons, and so the electron configuration would be 1s2, 2s2, 2p4, and as you can see in the 1s level, we have our 2 electrons. The 2s, we have our 2 electrons, and we get to 2p, we have upspin, 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 and then we come back and do the downspin. So that is the off-bow principle. And when you start getting to the D levels and so forth, you always put a single electrons in those suborbitals. The Pauli exclusion principle, no 2 electrons can have the same 4 quantum numbers. This really comes down to quite a bit. You start getting into the spins. No more than 2 electrons can occupy the same orbital, and 2 electrons same orbital must have opposite spins. So we can look at this one here. We see the 1s, we're looking pretty good in each of these 3. We have an up, spin, down, up, down, up, down. And then we get over to the 2s, up, down, which is good. The middle one here, we have 2 up spins, so that is incorrect. They got to have opposite spins. And likewise, you get to the third example here, it is incorrect because there are 2 down spins, or the spin down. And that would be the 4th quantum number. Hund's rule says the most stable arrangement of electrons and subshells is the one with the greatest number of parallel spins. So we look at this. Let's look at this. We have our 1s, we have an up and a down, and that's filled. 2s, up and a down, that's filled. 2p, we only have 3 electrons in the 2p, so each of these suborbitals will have 1 electron with the up spin. Could it be the down spin? Yeah, but you need to be consistent. The middle one, the 1s and the 2s are okay. But as you can see here, we have 2 electrons in that first suborbital in the p, and we left an empty one, so there would 1 electron would need to be moved over here. And it would also have to have a parallel spin. The third example, we get into the 2p, yeah, there's 1 electron, but they're all not parallel. As you can see, the middle one is a down spin, and the first and the second are up spins. Electron configurations, you've probably seen a bunch of different diagrams. This one's pretty popular. So the 1s gets filled, comes back around to the 2s, 2p, 3s, 3p, 4s, and then so forth. You can follow this. You see some, I'm going to call it out of order because these give it the most stable electron configurations. So as you go through this, you can see these are going to go ahead and fill. Another way to look at this is another example. We have the 1s, then the 2s. 2p could hold 6. Then we go to 3s, 3p. Notice the 4s is before the 3d, and the 3d we can hold 2, 4, 6, 8, 10 electrons. Go to the 4p, and you can see it. We start going through all the way up to the 6pa. Most of the problems you're going to see, especially in high school chemistry, will probably end up being in this range here, maybe up through the 6s. Well, that's it for this one. We're going to do some practice problems coming up, and we're also going to look at why chromium and copper have different electron configurations than you would expect. So until next time.